This is the Chapter 21 lecture outline video. This chapter is going to give us an introduction to modern astronomy. So it's going to cover a lot of material. There's 35 slides in this slideshow, and I'm going to try not to make this video more than 20 minutes long. All right, so we're going to start back with the ancient Greeks. So they used philosophical arguments to explain natural phenomena. I'll give you one example. Aristotle came up with two theories about falling objects. He basically said that heavier objects fall faster than lighter ones, and that there had to be a force applied to an object in order for it to be moving. Turns out that those arguments were not how it works, and it took about 2,000 years for those views to be basically changed and accepted by other scientists in the time period. So these arguments didn't work for a lot of things, but they did work for some things, and they did take some observational data. Now, most ancient Greeks held a geocentric view of the universe, meaning that the Earth was in the center. They thought the Earth was a motionless sphere at the center of the universe, and that everything else revolved around it. They did know that there were heavenly bodies that were not stars in the space. They called these seven wanderers. So the sun, the moon, Mercury, Venus, Mars, Jupiter, and Saturn. They basically thought that all of those things revolved around the Earth. All right, so Aristarchus was the first Greek to profess that a sun-centered or heliocentric view of the universe was the correct view. Planets exhibited an apparent westward shift, and we call that now retrograde motion. And this occurs as Earth, with its faster orbital speed, overtakes another planet. So Mars is farther away from the sun than the Earth, so it moves a little slower compared to the speed of the Earth. So it would actually seem like we would overtake Mars. So it looked like it would move westward as opposed to moving in the normal direction of the eastward. So the Ptolemaic system was around AD 141, and this was a geocentric model, so Earth-centered. And to explain retrograde motion, Ptolemy used two motions of the planets. He called the large orbital circles deferents, and these small circles called epicycles. So this is sort of a picture of that if we assumed Earth was in the center of our solar system. So all the other objects were moving around in an orbit called deferents, and then they had to also be moving around in smaller circles in order to match the observational data that the Greeks would actually look up in the sky and see how these things were moving. So this is obviously not how it actually is, but this was the universe according to Ptolemy in 2nd century AD. This is just an example about, since the Earth's moving faster than Mars, Mars would appear to move like this in the sky, so it would be moving this way, and then it looked like it would come backwards a little bit and then eventually move off in the original direction. So that was because Mars was moving a little slower than the Earth, so the Earth can actually overtake Mars over a long period of time in 1 year. All right, so the birth of modern astronomy happened in the 15 and 1600s, and there's 5 scientists to note, and I'll be going through each of these. We have Copernicus, Tycho Brahe, Johannes Kepler, Galileo Galilei, and Sir Isaac Newton. All right, Copernicus. So he concluded Earth was actually a planet and not the center of the universe. So he constructed a model of the solar system that had the sun at the center instead of the planet Earth. So this ushered out the old astronomy from the Greeks. So Tycho Brahe, he actually took a lot of data. So he actually was able to collect a lot of observational data from different things moving in the sky. He did not believe in the Copernican system, only because he was unable to observe something called stellar parallax, and this is just the shift in a star's position due to the revolution of the Earth. He wasn't able to take the data, so he couldn't, convince himself that the Copernican system was correct. And then we had Kepler. He ushered in new astronomy. He basically said that planets revolve around the sun, and he came up with 3 laws called Kepler's laws. So this is one of them. Don't worry about it too much, but it basically says that as one planet sweeps out a certain area during one time of the year, it has to equal the same area swept out from a different time during the year. As long as the time periods are the same, the areas have to be equal. So as an example, he just is showing you that when the planet is moving this part of the Earth in January, so 1 month, when the planet is moving this much area in July, these 2 areas have to be equal. So his other three laws also stated that the orbits have to move in elliptical orbits, not circular orbits. The planets revolve around the sun at varying speeds, and then there's a proportional relationship between the planet's orbital period. So this is the time it takes the planet to revolve around the sun once, and the distance away, the average distance away that the planet is from the sun. Then we had Galileo. He supported the Copernican theory. He also used experimental data. He also constructed a large astronomical telescope in 1609, where he was able to observe the four large moons of Jupiter. To him, planets appeared as disks. He also discovered the phases of Venus. He saw different features on the moon, and he was able to observe sunspots. Galileo also was the scientist that's given credit with refuting Aristotle's view of how objects fall. So just to review, Aristotle said that objects fall at a faster rate if they're heavier objects, and that you needed a force on an object to keep it in motion. So Galileo was actually able to show that all objects, regardless of mass, fall at the same rate, and we call that the acceleration due to gravity. And an object will continue in motion unless acted upon by a force. So you'll actually continue in continuity until a force acts upon you. So he was able to refute Aristotle's two philosophical arguments for how objects fall. And then we have Isaac Newton. So he came up with the law of gravitation, and he proved that the force of gravity, combined with the tendency of an object to remain in a straight line motion, he got that from Galileo, results in elliptical orbit, which was discovered by Kepler. And also in his spare time, he's credited with co-inventing calculus. I don't know how this guy, basically was able to have any fun, but I don't know. He was pretty busy in his lifetime. And this is just a picture showing you that he was able to rationalize that the gravitational force was the force keeping an object in its orbit, producing this elliptical orbit that Kepler said was one of his three laws for planetary motion. All right, so just a little information about constellations. So constellations are just configuration of stars named in honor of different mythological characters, creatures, or great heroes from Greek mythology and Roman mythology. So today, 88 constellations are recognized. They divide the sky into units, sort of like boundaries in the United States. And the brightest stars in a constellation are identified in order of their brightness by the letters of the Greek alphabet. So alpha, beta, and then so on and so forth. All right, so how do you figure out the position in the sky? So stars appear to be fixed on a spherical shell around the Earth, and we call this sphere the celestial sphere, and it surrounds the Earth. So to find any single position for a star, you only really have to know two things. You have to know something called declination. So this is the angular distance north or south of the celestial equator, and then right ascension. This is the angular distance measured eastward along the celestial equator from the position of the vernal equinox. So if you take a telescope and then start it at the equator, and then you move north or south at your declination angle, and then move to the right a certain amount of degrees, you'll be able to find any position in the sky just using those two angles. So it's a very easy system to identify different things in the sky, and it's very similar to the latitude-longitude system that could be used to identify any location on the Earth's surface. All right, so Earth motion. There's two primary motions of the Earth. One is rotation, and this is turning or spinning on the body on its axis, and we obviously know that the Earth rotates once every 24 hours. So there's two measurements. So we have our mean solar day. So this is the time interval from one noon to the next, which is about 24 hours. There is something else called a sidereal day. This is the time it takes for Earth to make one complete rotation with respect to a star other than the sun, and this time turns out to be 23 hours, 56 minutes, and 4 seconds. So not quite 24 hours, but it's close. And this is just showing you a representation of that, how it's slightly off from a regular solar day. The other Earth motion is a revolution. So this is the motion of a body around another body. So Earth's orbit is elliptical, but it's very nearly circular. So if you were to look at it and just look at it by inspection, you might say it's a circle, but it's actually elliptical, but it's very close to being a circle. So when Earth is closest to the sun, we call this perihelion, and that actually ends up to being in January. And then Earth is farthest from the sun, and that is in July. And the plane of the ecliptic is an imaginary plane that connects Earth's orbit with its celestial sphere. So here's just a picture of that. So you're going to see that That orbit, if you were to look at the top-down version of it, you might say that it was a circular orbit, but it's really elliptical. Other motions, so Earth precesses, and what does that mean? Well, this is a very slow Earth movement. It's very hard to detect, but this is the direction in which Earth's axis points continuously changes. So we know Earth's tilted on an axis, so it is going to be the direction in which that axis is pointing as the Earth rotates and revolves around the sun. So it's a very slow movement. And we move within the solar system itself in the direction of the star Vega, and our solar system revolves around the galaxy itself, and then our galaxy moves within the universe. So there's a lot of complicated motion that we don't really think about on a daily basis, but just think about that. We're rotating around an axis on Earth. We're rotating around the sun, revolving around the sun. Our sun is rotating within a galaxy. Our galaxy is then rotating within the universe. It's kind of a scary thought to think about, but there's lots of motion up there in space. This is just a diagram showing you what it means by precession. So if you think about a top, when you spin a top, it seems to be rotating around one location. That's what we mean by precession. So the Earth is kind of spinning like a top slightly, but it's a very hard motion to detect. All right, so we're going to end this chapter with the Earth-Moon system, just a little brief information about it. So we have a synodic month. So this is the cycle of a moon as it passes through its phases, and it's about 29.5 days, and it's based on the first Roman calendar. We also have a sidereal month. So this is the true period of moon's revolution around the Earth. So this is the actual amount of time it takes the moon to revolve once around the Earth, and it's 27.3 days. Again, just showing this diagram is just showing you the difference between the actual lunar month and then how long it actually takes the moon to revolve around the Earth. All right, so the difference of 2 days between the synodic and sidereal cycles is due to the Earth-Moon system also moving in an orbit around the sun. That's what that previous diagram was showing you as well. And then the moon's period of rotation about its axis and its revolution around the Earth are the same, so about 27 1/3 days. So this causes the same lunar hemisphere to always be facing the Earth. So we do have a dark side of the moon and then, obviously the light side. So some phases of the moon. When viewed from above the North Pole, the moon orbits Earth in a counterclockwise or easterly direction. So the relative positions of the sun, Earth, and moon constantly change. The lunar phases are a consequence of the motion of the moon and the sunlight that is reflected from its surface. So you might see a crescent moon, a quarter moon, a gibbous moon is when it's approaching to be a full moon, and then finally we have a full moon. All right, so this is because the position of the moon and the sun and the Earth are constantly changing. So different parts of the same hemisphere of the moon are being lit by the sun versus other directions. All right, the last part of this chapter is different types of eclipses. So the first type is a solar eclipse. So this is when the moon moves in a line directly between the Earth and the sun. And this doesn't actually occur that often. In the United States, we haven't seen a solar eclipse, I think it's since 1979, but I think we're due to have one actually this summer. At some point, there'll be a solar eclipse. And this is the type of eclipse that you're not going to want to look at with just your eyes. You're going to want to use a mirror or some other type of reflecting material to look at this eclipse. You're not going to want to look at it just with your eyes. So this is when the moon, it comes between the Earth and the sun. All right, and then you get a very strong, basically light show in the sky when this happens. And then the other type is a lunar eclipse. So this is when the moon moves within the shadow of the Earth, and this only occurs during the full moon phase. So the picture of this, so this is when the Earth comes between the sun and the moon. So the moon actually looks like it's in a shadow. So you actually have some color to it, and that's why during a lunar eclipse the moon can look red.